Yeah, so I would like to start with saying that I'm one of those people who randomly stumbled upon the Snoofer YouTube channel without knowing anything about the topic, and I just watched all videos basically, and that's how I got initially interested in the field, and that's how I eventually also found two great supervisors to help me get a PhD. So I guess I would say I'm really honored to be able to present here today. Yeah, so first I would like to start talking about the main paper that kind of inspired this work, which, yeah, the title kind of gives away what the paper was about. But the basic idea behind it was that if we embed neurons into space and we perform some sort of L1 regularization, then nothing interesting happens. But if we introduce an additional Euclidean distance-based cost to this regularization term, then loads of things emerge from this topology through training. The two main ones I guess I would like to highlight is that it becomes more modular and more small world, which does have implementation benefits as well, but it's also just a direct link to neuroscience properties. And I had a question, which I guess many other people had as well when they read this paper, is like, what if the neuron positions could be optimized? And what would happen in this case is that we would probably expect all neurons to collapse to the origin of the space, the center, because there's just no benefit of keeping long distances between neurons. And so now I'd like to turn to delays. So delays have been on interest, not just for me, but I guess generally for the field. Many people are interested in them currently. And it also has like neuroscience links. So for example, some people claim that these delays can be modified through myelin plasticity, which also happens connected to neuron activity. So it kind of is thought by some people to be a part of learning as well. But the kind of delays I would like to focus more on today is the ones that are related to the structure of the networks. And that has like neuroscience, that has a relationship with neuroscience findings as well. The most well-known example is this axonal delay line that has been measured in the owl brainstem, where they kind of showed that these delay lines are used for sound localization. And actually, just to highlight, some of us even worked on this sound localization circle with SNNs, with delays, but we didn't focus too much on the structural aspect of things. So I would like to talk about this event-based delay learning algorithm that I worked on before in my PhD, or I'm still working on it, but yeah, so like this aspect of it is already done. So using the event prop formalism, we derived delay learning for leak integrate and fire neurons, and we get these scary looking update equations or backward dynamics, but the update equations themselves, both for weights and for delays in the system, are really efficient because they only happen at spike times. And this is really cool, but for this talk, the more important aspect of this is that within this framework, we can also calculate recurrent delays using gradient descent. And when we actually looked at these recurrent delays, what we found is that if we trained networks where we had those recurrent delays and they were learned, so these are examples from the spiking Heidelberg digits, the spiking speech commands, and the Braille letter reading datasets. And if you look at the lower parameter ranges, so for when we really compress the hidden layer, then these recurrent delays, so the blue dots here, become really useful. So it kind of shows that, like, okay, maybe they might be good for something. And actually, since then, another recurrent delay method has been introduced very recently, where they also showed that introducing these recurrent delays is quite useful. So I don't know if it's clear at this point where I'm heading with this, but the core idea is that maybe we could connect these to space by defining these delays as the Euclidean distance between neurons. So for example, if we have neuron J and neuron I in 3 dimensions in this example, then we would define a delay as this. And then if we again take our previously shown delay gradient update rule, then we can just plug these 2 equations together, or plug one in the other, and we end up with this delay gradient update rule, which maybe intuitively, I guess it says a bit that it's like a combination of the presynaptic and postsynaptic delays with some term that normalizes based on distance, basically. And so what changes about this learnable delay matrix is 3 main things, which come from these Euclidean properties. The first is that we have 0 diagonals. This one, I guess, isn't it's like relatively clear what happens. So if we if we have a zero delay in the diagonals of this delay matrix, that just means that the updates for the autoptic connections will take effect immediately in the next time step. So it becomes the reset basically. And we have symmetry, which means that from neuron I to neuron J, the delay will be the same as the way back. And the third one is the triangular inequality, which means that the fastest path to another neuron is always the direct one. So we can't like skip through like a shorter, connectivity pattern basically to another neuron. It will always be, the fastest path will always be directly spiking or sending a signal to the other neuron. And so from here on, I will focus specifically on networks that were trained on spiking Heidelberg digits with a single hidden recurrent layer. And in this hidden recurrent layer, the neuron positions were optimized with the previously shown update rule. And first, we just wanted to measure is this too strong of a constraint, the 3 that I show here? Is the network still even capable of learning something useful? And one more thing that I would like to highlight is that we also compress our 3 parameters in this network. So beforehand, we had n times n delays, and now we have n times d, where d corresponds to the number of dimensions in space. And what we find is that basically, yes, they are useful. So we compared to a couple of different networks, different embedding sizes, different hidden layer sizes. And if we look at the most important comparison here is comparing the green dots to the blue dots. So the green dots are the networks with just plain recurrence, no delays. And the networks where we do have these delays derived from the Euclidean distance between neurons, those seem to outperform the other networks in all cases. So I guess the thing that we should take from this is that we're good to go. Basically, through position learning, we're probably learning something that is useful, and thus it's interesting to look at what we actually learned. So first, we wanted to look at how these hidden neurons connect specifically to these input neurons. So the first one we tried is we performed a regression where from each hidden neuron, we tried to predict what its position will be with knowing what its input connectivity pattern is. So in spiking Heidelberg digits, we have 700 input neurons. That means for each hidden neuron, we have a 700 long or a vector containing 700 elements. And from that, we would try to predict x and y coordinates. And at initialization, we can't do this too well. But then when we look at the other networks, so the ones that I mentioned before, a network without any regularization, or L1 regularization, or L1 regularization with a distance cost, in all of these cases, we can predict this better, kind of implying that just by knowing an input connectivity pattern, we already kind of know in what space, in what physical space that computation will happen, basically. And next, coming from a similar place, we also wanted to do some visualization. So this is an example from the spiking Heidelberg digits dataset. On the x-axis, we see time, and then the y-axis, it's the input neurons. And we color-coded these 700 input neurons. And first, we tried to look at if each of these input neurons have like I refer to them as a preferred position in space. And the way we do this is we calculate a center of mass, but we weight each of the positions of the hidden neurons, with its corresponding input to hidden weight. Which, yeah, as I said, basically the best way to think about it is this will give us like where would this specific input neuron like its computations to happen in the hidden space. And here's an example from one of the trained networks of what we see. So I think visually this is quite telling. So we see that neurons that are close to each other in the input in the input space, so basically closer frequencies, tend to want to their computations happen in a similar space in the physical space in the hidden layer. And we also wanted to do this not by looking at the learned weights, but we also wanted to measure after training how sensitive do hidden neurons become to specific input neurons. And I won't go into detail how we specifically define this metric. It's kind of like inspired by a spike-triggered average, but basically we end up with an activity-based matrix, or a matrix that's derived from the activities of neurons, which also tells us like how sensitive hidden neurons are to input neurons. And we also did this weighting kind of visualization again. And here we even get like an even smoother trajectory. It's kind of even surprising that it ended up being so smooth. Intuitively, I still don't have an explanation of why this emerged, but again, we kind of see that like similar computations are basically happening in similar spaces in the physical space. And finally, we also looked at this over time. So by measuring the sensitivity for each time step, and it also gives us a visualization of like what neurons are the most important in the computation at what time, and where are those computations happening in space. So we see that initially it starts from like relatively in the middle, focusing on all kinds of neurons, and it collapses into the center in the trial, where it focuses more on the lower frequencies, and then towards the end of the trial again, it spreads out, and now it's focusing maybe a bit more on higher frequencies again. And so next we looked at some training dynamics of these networks. So we specifically compared networks with L1 regularization and L1 regularization with the distance cost, and a network that had nothing to do with space, and it was like doing just like free synaptic delay learning. And at first, if we just visualize the training process, we see that all of these neurons, regardless if we have this cost term or if we don't, they all go towards the perimeter of the space that we fix them in. But since something I didn't say is that we denote like these synaptic strengths with line thickness, and we see if we don't introduce this cost term, then also we have more longer strong connections, and if we introduce the cost term, then we have less of them basically. And we measured a couple of metrics over training dynamics or throughout training. And the first one we measured it was this Q metric, which is equivalent to modularity basically. And we see that we need to introduce this cost term to achieve higher modularity. Then we also looked at the entropy of these learned weight matrices, where we see that already by embedding neurons into space and learning their positions, we already achieve a slightly lower entropy in our weights. But again, introducing this cost term even increases it further. But we can also calculate this entropy not just on the actual weights, but we can also calculate it on the communicability matrix, which is derived from these hidden weights. And then we achieve a lower entropy again for this the network where we introduce this distance cost. And finally, we also looked at small worldness, where again we see that introducing the cost term achieves a higher modularity, or sorry, higher small worldness. But interestingly here, if we don't have the cost term, the spatial network achieves a lower small worldness metric than the network that has nothing to do with space. And so finally, we were interested in, so like in all of these examples, I was talking about networks where we introduced L1 regularization or a distance cost, or the combination of these two. But we were also interested in, can we understand anything from networks where we don't employ anything like this? And so I guess like the relatively obvious way of looking at this is like, what can we prune away in the network, or which are like the most important weights that were learned or that were optimized. And so we did kind of the kind of obvious things with magnitude-based pruning and random pruning, and neither of these had an effect, or like they didn't really show a difference between networks where we learned the positions and where we implemented free synaptic delay learning. But if we instead do this pruning based on the delay length, then we see that the performance in the non-spatial network breaks down much faster than it does in the spatial network. And maybe looking at the learned delay matrices kind of shows why this is the case. So with the position learning or the spatially embedded networks, these delays are kind of concentrated in this lower range of values. And in the non-spatial network, it kind of is more like a long-tail distribution with loads of values at 0. And we also measured the modularity and small worldness on these as well. And not surprisingly, when we perform a delay length-based pruning, then the modularity and small worldness increase much more in the position learning networks. And so as a conclusion, I would, yeah, maybe I'd say these two things, that position learning networks converge in more local solutions, and they also become more modular with spatially closed neurons focusing on similar parts of the input. But I guess also something I would like to highlight is that if you have these spatial networks, you can do visualizations like the one on the right, which maybe from a scientific perspective, it's not super useful, or I don't know, but it does look cool. And yeah, so I would like to thank you for your attention. I would like to thank my supervisors, Jamie and Thomas, for helping, and Dan as well, who yeah initially inspired this work. And apologies to all of them for I just realized that these are all really low resolution pictures that I found of them. But yeah, the preprint of this work is available with the same title if you search an archive. And yeah, I'm happy to hear your questions.
Great. Thanks, Balázs. Very interesting stuff.
Oh, and also, sorry, one more thing.
Right.
I just realized that since I'm talking with you as well, I had the opportunity to talk about this in Dan's lab as well, and Dan Goodman, the person I'm talking to now, not the Dan who actually helped with the work, but Dan Goodman and Gabrielle, they had really insightful comments, and it was really, really helpful. So thank you to you as well.
Cool. Okay, I'll ask some of the questions from the chat. The first one that I'll ask is from Michelangelo, and he says, "Did you try and relate your delays to the length of axonal paths?"
Um, I'm not sure I understand the question. What do you mean by axonal paths?
I wondered. So I had a question in mind, which was to say that you've got if you say that the spatial thing is equal to the delay, that
Mhm.
means that you've got a fixed conduction speed.
Yeah, yeah, yeah.
So maybe that's something the question is getting at that.
Then I guess we didn't. So like the only way that this can be interpreted is that the distance between two neurons is exactly the difference or exactly the delay that will emerge between them. So we don't focus on axons, we don't focus on myelination. This is purely derived from the distance between neurons. And I guess it would be interesting to introduce these other things as well. But it kind of like I think we have to constrain this problem to some extent because if myelination can occur, then maybe yeah, then probably all of these spatial things suddenly don't make too much sense anymore because then they're again free to do whatever they want through learning.
Cool. So the next question was from Tim Masquelier. He asks, I guess you don't respect Dale's law,
No.
i.e. having separate inhibitory and excitatory neurons. And do you think it would change the spatial organization after training?
Yeah, I would imagine so. I didn't really look too much at if these learned weights end up. Yeah, like I didn't look at the connection between positive and negative weights and delay lengths and all of these things. But I would imagine that, yeah, definitely it would have an impact. And yeah, it's a good point, and I'd definitely be happy to try that as well.
Cool. Okay, I think we've got time for just one last one, which is from Napat Sahapat. Have you looked into adaptive hyperneat in CPPN, which learn weights based on XY coordinates in 2D space? So I
No, I've
guess it
not
would be a
even heard
kind of
of
a
them.
generalization.
Yeah, it sounds really cool. I'll look it up right after Snooper. No, I haven't looked into them. Thank you for highlighting it.